What if reality doesn't exist until someone looks at it? Not metaphorically, not philosophically, literally. Somewhere in a physics lab right now, two scientists can run the exact same experiment, follow the exact same rules, and walk away with two completely different, mutually exclusive versions of what just happened. And both of them would be right. Sit with that for a second, because it is not a trick of language. It is not a riddle with a clever resolution waiting at the end. It is one of the strangest, most stubborn problems in modern physics, and it has a name. Physicists call it Wigner's friend. Once you understand what it actually claims, you will start to wonder whether the solid, dependable, agreed-upon world you wake up in every single day is really as solid as it feels. Let's start at the beginning, because the story behind this paradox is almost as strange as the paradox itself. In 1961, a Hungarian-American physicist named Eugene Wigner sat down to write something he called a partly baked idea. Wigner was not a crank. He was a towering figure in 20th century physics, a Nobel Prize winner, a man who had helped shape our understanding of the quantum world from its earliest days. And yet, here he was, publishing a thought experiment so unsettling that it would still be debated, tested, and argued over more than 60 years later. Wigner's idea was deceptively simple. Imagine a friend of his sealed inside a soundproof laboratory. Inside that lab, the friend performs a routine quantum measurement. Maybe it's an atom that can decay or not decay. Maybe it's a photon that can spin one way or another. It doesn't matter exactly what the experiment is. What matters is what quantum mechanics says happens before that measurement is made. According to the strange mathematics of quantum theory, before an observation occurs, a particle does not have to pick a single state. It can exist in something called a superposition, a kind of blurred, unresolved condition where it is simultaneously in more than one state at once. Decayed and not decayed. Spin up and spin down. Both at the same time until something forces it to choose. That something, in the traditional understanding of quantum mechanics, is a measurement. The moment an observer looks, the superposition collapses. The particle picks one outcome, and reality snaps into focus. This is the basic backbone of quantum theory, as it's taught in nearly every introductory physics course on Earth. So in Wigner's thought experiment, his friend inside the lab makes the measurement. From the friend's point of view, the story is simple. She looked at the particle, it collapsed into one definite state, and now she knows the result. As far as she's concerned, the experiment is over. Reality has resolved itself. There is no more mystery here, no more blur, no more superposition, just a fact. But now step outside the lab and stand where Wigner is standing. From Wigner's perspective, he has no access to what happened inside. The lab is sealed, no information has escaped. As far as the rules of quantum mechanics are concerned, if he hasn't personally observed the outcome, then technically nothing has collapsed for him. Which means that from his point of view, the entire lab, including his friend, including her mind, including her memory of having seen a result, must be treated as being in a superposition, not just the particle, everything entangled with it. That means, in a very real sense, according to the math, his friend exists in two states simultaneously, having seen one outcome and having seen the other outcome, until Wigner opens the door and looks for himself. Now here is where it gets genuinely disturbing and where the paradox earns its reputation. Ask the friend inside the lab what happened, and she will tell you with complete confidence that she saw a specific, singular result. She's not confused. She's not guessing. As far as her experience is concerned, the collapse already happened the instant she looked. There was no blur, no superposition, no ambiguity in her memory. Ask Wigner, standing outside, and mathematically, he is entitled to describe the entire scene, his friend included, as an unresolved superposition of two contradictory outcomes, right up until the moment he opens that door. Both descriptions are internally consistent. Both follow the accepted rules of quantum theory to the letter, and yet they flatly contradict each other. The friend insists reality already picked one path. Wigner's own equations say it hasn't picked anything yet. Someone has to be wrong. Except, according to the mathematics, nobody's wrong. That's the paradox. That's the trap. Two valid descriptions of the same physical situation, produced using the same rules, arriving at completely different pictures of what is real. For decades, this was treated mostly as a philosophical curiosity, something physicists brought up at dinner to sound clever, but not something anyone expected to actually test in a laboratory. After all, how do you seal a conscious human being inside a superposition and then interrogate them about it without collapsing everything the moment you try to look? It sounded like an experiment that could only ever exist on paper. Then, starting in the last decade or so, something changed. Physicists realized they didn't need an actual human being trapped in a box to probe the guts of this paradox. They could substitute something much smaller and far easier to control. A single photon, a particle of light, could stand in as a proxy for the observer. If a photon measures another particle in a very specific and carefully engineered sense, then you can treat that photon as a miniature stand-in for Wigner's friend, And you can test what happens to the whole system from an outside perspective. And that is exactly what several research teams have now done. Using entangled photons and increasingly sophisticated setups, physicists have built laboratory versions of extended Wigner's friend scenarios, some involving not just one friend, but multiple friends, nested inside layers of observation, like a set of Russian dolls made of light and probability. These experiments have actually been carried out. They are not hypothetical anymore. The results did not resolve the paradox. If anything, they sharpened it. The experiments confirmed that the strange, seemingly contradictory predictions of quantum mechanics hold up even in these more elaborate multi-observer setups. The mathematics keeps giving you two incompatible stories about the same event, and both keep checking out. Naturally, not everyone is convinced that using a photon as a stand-in for a conscious observer is a fair test of what Wigner originally meant. Some physicists have pushed back hard on this substitution. One prominent critic has called the use of photons as observers essentially absurd, arguing that a genuine friend in this thought experiment has to be something macroscopic, something closer to an actual person, or at least a large, complex physical system, not a single, fragile particle of light. Others have pointed out that nobody seriously believes a photon has anything resembling awareness, memory, or a point of view, so treating it as equivalent to a human observer might be smuggling in an assumption that quietly changes what the experiment is actually proving. That criticism is fair, and it matters. But here's the uncomfortable part. Even the strongest critics of the photon substitution generally don't argue that the math is wrong. They argue about interpretation, about what counts as a legitimate observer, about where exactly the line between quantum system and conscious mind should be drawn, the formal structure of the paradox, the part where two valid frames of reference can produce contradictory pictures of reality, remains intact no matter how you draw that line. It also helps to see how Wigner's friend fits alongside its more famous cousin, Schrödinger's cat. Schrödinger, back in the 1930s, imagined a cat sealed in a box with a vial of poison triggered by a random quantum event. Until the box is opened, the story goes, the cat is neither alive nor dead, but somehow both. A superposition of two contradictory states. Most people who've heard of quantum mechanics at all have heard some version of that image. But Schrödinger's cat, as unsettling as it sounds, is really a story about a single observer in a single moment of collapse. Open the box, look inside, and the ambiguity resolves. Wigner took that same unease and pushed it one level further. He didn't just ask what happens to the cat before you look. He asked what happens when the person looking is, themselves, being watched by someone else who hasn't looked yet. That extra layer is what turns a strange but containable puzzle into something with no obvious floor. Once you allow a second observer to also be treated as an unresolved quantum system, you open the door to the same question at every level. What if that second observer is being watched by a third and a fourth, and so on? Nothing in the mathematics tells you where, if anywhere, this chain is supposed to stop, or which observer, if any, gets to be the one whose look finally counts as final and real. There's also a strong family resemblance here to another classic result in quantum foundations, the Einstein-Podolsky-Rosen paradox and the Bell inequality tests that followed it. That earlier line of research asked whether two distant entangled particles could really be correlated with each other without some kind of faster-than-light influence passing between them, or whether instead they'd been carrying hidden, predetermined properties all along. Decades of increasingly precise experiments came down firmly against the idea of simple hidden variables, confirming that quantum correlations really do defy the kind of local, common-sense picture Einstein originally hoped for. Wigner's friend isn't identical to that older puzzle, but it grows from the same unsettled soil. Both paradoxes take assumptions that feel almost too obvious to state out loud, that reality is local, that facts are singular, that an outcome, once fixed, is fixed for everyone. And both show, through rigorous experiment and equally rigorous mathematics, that at least one of those comfortable assumptions has to give way. And that same discomfort, common sense colliding with careful mathematics and losing, keeps drawing physicists back to this entire cluster of paradoxes, generation after generation. And it's that formal structure that has pushed things from a curious thought experiment into something with real teeth. In recent years, physicists have gone beyond simply describing the paradox and started proving, with rigorous mathematical arguments, that certain comfortable, common-sense assumptions about reality simply cannot all be true at the same time. These are sometimes called no-go theorems, and they function a bit like a mathematical vice. They take assumptions that feel obviously true, things like an observation once made is a fixed and unique fact of the universe, and they show that you cannot hold on to all of them simultaneously without running into a contradiction with the predictions of quantum mechanics. Think about what that actually implies. Ordinarily, we assume there is one objective world, ticking along the same way for everyone. My memory of last Tuesday and your memory of last Tuesday might differ in detail, but we assume there's a single underlying reality that both of our memories are approximately describing. Wigner's friend, especially in its newer, more rigorous forms, chips away at that assumption. It suggests that in specific quantum scenarios there may not be one single fact of the matter about what happened. There may only be facts relative to a given observer, facts that are true for the friend inside the lab, but not yet true for Wigner outside it. Facts that depend on your vantage point in a way that goes far beyond simple ignorance or lack of information. This is not the same as saying different people have different information and therefore disagree. That kind of disagreement is mundane. Two witnesses to a car accident might genuinely see different things because they were standing in different places. Quantum theory is claiming something stranger. It's claiming that there might not be a single complete story sitting underneath those two viewpoints waiting to be uncovered. The disagreement isn't a gap in information. It might be a genuine feature of reality itself. That is the sentence that keeps physicists up at night. Not the technical mathematics of Hilbert spaces and density matrices, but the plain, brutal implication sitting behind it. If facts can be relative to an observer in this deep, fundamental sense, then the entire notion of one shared objective universe, the same for everybody, might not survive contact with quantum theory at the deepest level. Naturally, physicists have not simply thrown up their hands. Over the decades, several major camps have formed, each offering a different way to make sense of or escape from the paradox. One approach leans on something called decoherence. In the real world, nothing is ever perfectly isolated. Particles constantly interact with their environment, bumping into stray photons, air molecules, thermal vibrations, and all of that messy interaction tends to destroy delicate quantum superpositions extremely quickly for anything larger than a handful of particles. Decoherence theory argues that a human being, or even a complex measuring device, is so thoroughly entangled with its environment at every instant that treating them as existing in a clean, isolated superposition, the way Wigner's thought experiment requires, is simply unrealistic. In this view, for all practical purposes, the friend's measurement really is final and definite almost the instant it happens, because the surrounding environment has already measured it too, spreading the information so widely that reversing it or meaningfully treating it as still undecided becomes essentially impossible. It's an elegant answer, and it explains a huge amount about why we never see cats, or friends, in visible superpositions in everyday life. But critics point out that decoherence doesn't fully dissolve the philosophical puzzle. It explains why the superposition becomes practically unobservable, not why, formally and mathematically, one specific outcome becomes the single true fact of the matter rather than just one branch among many. Which brings us to a second major camp, one with a much wilder reputation, the many worlds interpretation. In this view, there is no collapse at all, ever, for anyone. When the friend measures the particle, the universe doesn't pick one outcome and discard the other. Instead, reality itself splits. There is now a version of the friend who saw one result, and a separate, equally real version of the friend who saw the other result, each existing in their own branch of an ever-multiplying cosmic tree. Under many worlds, Wigner's paradox essentially dissolves, because there was never a genuine contradiction to begin with. The friend and Wigner aren't disagreeing about a single shared reality. They're each correctly describing their own branch, and the appearance of paradox comes from mistakenly assuming there's only one branch to describe. It's a strikingly clean solution mathematically. It's also, for many people, deeply unsettling, because it implies that every quantum event you've ever been part of has been quietly splitting you into countless divergent copies, each experiencing a slightly different universe, none of them aware of the others. A third camp takes a very different route entirely, arguing that quantum states were never meant to describe an objective external reality in the first place. This view, sometimes grouped under the label of relational or participatory interpretations, treats a quantum state not as a description of the world out there, but as a description of one observer's knowledge or one observer's relationship to a system. Under this framing, of course, Wigner and his friend give different descriptions. They're not describing the same thing at all. They're each describing their own information, their own relationship to the particle. The apparent contradiction was a category error from the start, like arguing over whether a coin is really heads when two people are looking at opposite sides of it. Supporters find this satisfying because it resolves the paradox without needing multiplying universes or exotic collapse mechanisms. Critics find it deeply uncomfortable because it seems to strip away the idea that physics is describing a single mind-independent universe at all, and instead reduces it to a web of subjective, observer-relative accounts. None of these camps has won. Decades of debate, careful mathematics, and now real laboratory experiments have narrowed down what's logically possible, but they have not delivered a knockout blow to any of the major interpretations. And that, more than any single experiment, is what makes this paradox so unnerving to people who have spent their careers inside quantum theory. This isn't a case of scientists simply not yet knowing an answer that's clearly out there waiting to be found, the way we don't yet know the exact mass of a neutrino, but expect to pin it down eventually with better instruments. This is a case where the very structure of the problem seems to resist a single tidy answer, no matter how good our experiments get. And the paradox hasn't stayed confined to a tidy corner of quantum foundations research either. In the last few years, physicists have started drawing surprising, almost uncomfortable connections between Wigner's friend and some of the deepest open problems in all of physics. One line of research links the paradox directly to the black hole information problem, specifically what's known as the firewall paradox, a separate and equally thorny puzzle about what happens to information that falls into a black hole. Researchers have argued that at a structural level, the firewall paradox and Wigner's friend paradox are, in a precise mathematical sense, the same problem wearing different costumes. Both hinge on the same underlying tension. Different observers, occupying different vantage points relative to some boundary, seem forced into fundamentally incompatible descriptions of the same physical situation. If that connection holds up, it suggests that whatever's really going on with Wigner's friend isn't some quirky side effect of measuring tiny particles. It might be pointing towards something much more fundamental about how information, observation, and reality relate to each other across all of physics, from a sealed laboratory all the way out to the edge of a black hole. Other recent theoretical work has pushed the thought experiment into even stranger territory, exploring what a Wigner's friend scenario would even mean near an actual black hole horizon, using it as a fresh angle to argue for or against certain deep principles about how different observers' descriptions of reality must ultimately fit together. Meanwhile, some 2026 research has pushed back in the opposite direction, arguing that the unsettling core of the paradox isn't actually unique to quantum mechanics at all. These researchers constructed purely classical thought experiments involving duplicated agents rather than quantum superpositions, and showed that many of the same unsettling conclusions about observer-relative facts can be reproduced without invoking quantum weirdness whatsoever. If that argument holds up, it would suggest something almost more disturbing in a different way, that the trouble was never really about quantum mechanics specifically. It might be a much deeper problem about the very concept of an observer, one that was always lurking underneath classical physics too, and quantum mechanics simply happened to be the place where we finally noticed it. So where does that leave us? Is reality actually different depending on who's looking? Are there really countless branching versions of you splitting off every time a radioactive atom decides whether to decay? Is the whole idea of the friend a category error dressed up as a paradox? Honestly, nobody knows for certain, and anyone who tells you otherwise with complete confidence is probably overselling their favorite interpretation. What we can say is this: the mathematics of quantum mechanics, tested now in real laboratories with real entangled photons standing in for Wigner's friend, keeps producing results that are fundamentally difficult to reconcile with a single, observer-independent picture of reality, at least not without adopting some genuinely strange auxiliary assumption, whether that's branching universes, relational truths, or some other exotic escape hatch. The rigorous no-go theorems built around this paradox have systematically closed off some of the easier, more comfortable ways out. You cannot simply wave your hands and say, it's just about limited information, and expect the mathematics to agree with you. Something deeper is going on, and it resists every attempt so far to tame it into something intuitive. It's worth stepping back and asking why this particular paradox, more than most others in physics, generates this specific flavor of unease among the people who study it. Physicists are generally comfortable with weirdness. Quantum mechanics has been throwing counterintuitive results at them for over a century, and most researchers develop a kind of professional numbness to it. Particles tunneling through barriers they shouldn't be able to cross, particles behaving like waves, and then like solid points depending on how you look at them, entangled particles instantaneously correlated across vast distances in ways that still don't allow information to travel faster than light. These are all deeply strange, and physicists have largely made peace with them because, at the end of the day, they don't threaten the idea that there's still one consistent shared reality underneath all the strangeness, even if that reality behaves in bizarre ways. Wigner's friend is different because it doesn't just say reality is weird. It threatens the assumption that there is a single reality to be weird about in the first place. That's a much scarier proposition because almost everything else in science, every experiment, every theory, every attempt to build a coherent picture of the universe quietly assumes that there's one objective world out there for all of us to investigate together. If that assumption turns out to be wrong, or even just conditionally wrong under certain quantum circumstances, it doesn't just complicate one narrow corner of physics. It pulls at a thread that runs through the foundation of the entire scientific enterprise. And this is precisely why so much careful, patient work continues on this problem, year after year, decade after decade, largely outside the public eye. It's not glamorous work most of the time. It involves painstaking mathematical proofs about which combinations of assumptions are logically compatible, delicate optical experiments involving carefully entangled photons cooled and shielded from every stray source of noise, and endless philosophical back and forth about what words like observer, measurement, and fact are even supposed to mean at the most fundamental level. But buried inside all of that painstaking effort is a question that reaches far beyond any physics department. What is real? Is it the same for everyone, everywhere, all the time? Or does reality itself, in some strange and still poorly understood way, depend on where you're standing when you look? Eugene Wigner never got a definitive answer to the puzzle he sketched out in 1961. He died in 1995, more than a decade before some of the most sophisticated experimental tests of his idea would even become technologically possible. He called his own proposal a partly baked idea, and in a sense, it still is. More than 60 years later, still being tested, still being argued over, still refusing to fully resolve. But that half-baked idea has aged into one of the most productive, most genuinely unsettling threads in all of modern physics, one that stretches from a sealed thought experiment laboratory all the way to the event horizon of a black hole. Maybe someday there will be a clean resolution. Maybe decoherence, examined closely enough, will turn out to dissolve the paradox after all. Maybe many worlds will be vindicated, and we'll have to make peace with the idea that reality is constantly, silently splitting around us. Maybe some entirely new interpretation, not yet invented, will come along and make the whole debate look like a misunderstanding from a more primitive era of physics. Or maybe, and this is the possibility that unsettles physicists the most, there simply isn't a comfortable resolution waiting for us. Maybe the deepest lesson of Wigner's friend is that the universe was never obligated to hand us a single, tidy, observer-independent story in the first place, and we've just now, after a century of quantum mechanics, started to genuinely reckon with what that might mean. So the next time you glance across a room at someone else, watching the same event unfold in front of both of you, it's worth pausing on the strange possibility sitting quietly underneath that shared moment. As far as anyone can currently prove, at the deepest level physics has managed to probe, you might not actually be witnessing exactly the same reality after all, and whether that thought excites you or terrifies you probably says a great deal about how you feel about the universe agreeing to keep its secrets, even from the very people who've spent their entire lives trying to pry them open.